All right, so we're looking at how many solutions each of these types of equations might have. So the first one is linear. Now you don't actually have to go through the whole process of adding 10 and then dividing by 4. You can already kind of know how many would you expect. Yeah, this one should just have one solution. Because in our different types of equations that we've solved, we've seen some that have one solution, some that have two solutions, and even a few that have no solutions. So it's always going to be one of those at this point. So for the second one, the absolute value, is this one of those that's going to have more than one solution? Yes. Yes it will. This one's going to end up having two solutions. But that's kind of how you approach it and how you decide. You see, is this function type one of those where you're going to have more than one solution? And absolute value is one of those. The reason is because after we move the 5 over, you would then split it into two different equations. In this particular case, that would mean you'd have x plus 2 equals 12 and x plus 2 equals negative 12. That's how we get rid of the absolute value. Then for the third one, we're dealing with a quadratic here. So when solving a quadratic, how many solutions would you expect? Two, yes. So when solving this, we would subtract the one from both sides, and then we would take the square root. When you take the square root of both sides of an equation, that's where you get two solutions again. And so for the third one, you have a square root equation. How many solutions would you expect for this one? One on this. Because when we square both sides, which is what we're going to do in order to get rid of the square root there, we still just have one answer. In this case, we started with the square root, so there's one solution. In the case of this third one here, we would take the square root of both sides. When you introduce a square root on your own, that's what creates the two solutions. If you start with a square root, it's still just the one solution. Now, having done that, we're going to get back to some fraction work that we've done, and we're just going to extend it out a little bit. Today, we're going to be dealing with fractions that look like these. Go ahead and write down that first problem here, and we're going to be working through it. So we're looking today at fractions that involve linear binomials. That is, within our fractions, somewhere in there, we're going to have an x plus or minus something. So for that first one, our instructions tell us to simplify it. Well, to simplify that, there's no addition, subtraction, multiplication, or division to do. So since all we're doing is just starting with the fraction, we're going to reduce it. And so in order to reduce the fraction, we look and see what can I divide all three terms by. Notice it has to be every term on the top and the bottom. So what can you divide 24, 12, and 16 all by? 6, nope, not quite. What else? 4, yeah. 4 goes into 16, 6 doesn't. So that's why it's going to be 4 here. So I'm now going to divide all three of those by 4. So 24 divided by 4? No, it's 6, yes. 12x divided by 4 is... What's 12x divided by 4? It's going to be 3x. If there's an x in the original, you're going to have an x in the result. Then it's minus. Notice the minus from the original carries through exactly as it was. And then the 16 divided by 4, that's going to be 4. So we got 6 over 3x minus 4. Now, having done that, before I call this one done, I want to take a look. And in the case of this second one, what can we divide 15, 30, and 20 all by? 5, absolutely. So I'm now going to go through, I'm going to divide all three of those by 5. So 15x divided by 5, that'll be 3x. The minus stays a minus. The 30 divided by 5 gives us 6. And then 20 divided by 5, that gives us 4. So this is our final answer. Again, you notice it happens to give us 3, 6, and 4 again. Again, there's nothing I can divide all of those by, which is why we know we're done. Next up, we're going to now add fractions involving these linear binomials. So, of course, start by writing down the problem. All right, and if we're going to do this addition, the very first thing we need is what? What do you always need when adding fractions?
Common denominator.
Common denominator, yeah. We need a common denominator. Now, do we already have a common denominator?
Yes.
Yes. The bottoms are already the same. So that makes our lives easier. We already know that when I add them, it's going to be 2x minus 9 on the bottom. Now, since I already had the common denominator, I can now add on the top. So on the top, I got 13 plus 4x plus 7. Combine the like terms. And between those, the 13 and the 7 are like terms. The 4x, there's no like terms that go with the 4x, so the 4x is just going to stay a 4x. And then the 13 plus a 7 gives us 20, so it's 4x plus 20. And then we still do want to check and make sure that it cannot be reduced anymore. So I now look at, in this case, all 4 terms. Is there anything I can divide 4, 20, 2, and 9 all by?
No.
No. It's close. I can divide 3 of them by 2, but I can't divide all 4 of them by 2. So that is as good as it gets. Okay, next up. Now let's take a look at multiplying these. So write down that problem. And then the first thing we do is we think about how to approach it, is we think about what is the rule for multiplying fractions. The same rule that would work if they were both numbers works when we have the x and all that in there. To multiply fractions, we're going to multiply straight across the top and straight across the bottom. So on the top then, I'm going to do 3 times 5, which is 15. On the bottom, I'm doing x plus 2 times 4. Now, a little note on this. Since I'm multiplying the whole x plus 2 by 4, it's the same thing as if I wrote it that way, which makes it a little bit easier to see why we have to multiply the 4 by both terms. Because that 4 is multiplying by both the x and the 2. And so 4 times x gives me 4x, and the 2 times the 4, that gives me 8. So I got 15 over 4x plus 8. Then we look to see, can that be reduced? Can I divide 15, 4, and 8 by the same thing? No. So that one is done. That's our final answer there. Next up, we're going to take a look at how we would approach it if it was division. So write down this problem. And we start again by thinking about what is our rule. Our rule for division is always the same. The rule for division is we always flip the second fraction. In this case, that's going to turn 5/4 into 4/5. And when we flip it, we change the division into multiplication. The first fraction, when we do that, is unaffected. The first fraction always stays the same in that. Now, technically speaking, what we're doing is we're saying we multiply it by the reciprocal. That's just fancy math speak for saying flip the second fraction and change it to multiplication. All right, so now it's a multiplication problem just like the last one. So go ahead and finish that one out. Go ahead and do the multiplication. Then on the top, we do 3 times 4. That's just going to be 12. And on the bottom, remember, you got to multiply both of them by the 5. So 5 times x gives me 5x. Plus stays a plus, and the 2 times 5 gives me 10. And then we look at that and we see, can it be reduced? So can I divide 12, 5, and 10 all by the same number? No. So that means that one's done. All right, now we start hitting ones that can sometimes be a little bit trickier to deal with. Please write this problem down. Then we'll see how do we add them when they don't start with the common denominator. Of all the problems that we're going to be taking a look at, this is probably about the trickiest of them. It's still not even going to be too tricky. It's just a matter of learning how do we deal with it. All right, so then in order to do it, we do need that common denominator first. And again, I know I need a common denominator because it's addition. You only need a common denominator with addition and subtraction. And by the way, we aren't doing any examples with subtraction here, but subtraction works exactly the same as addition. The only difference is you subtract instead of add. All right, so first thing I do need is that common denominator. In this case, because this is an x plus 2, and this is a 4, it might be tempting to think, oh, well, I can just turn the 2 into a 4. But you'd still have this x plus with it. And so I need to have an x plus something in this one as well. So when you're faced with this sort of a situation, in order to get the common denominator, just multiply them by each other. So in this case then, I'm going to multiply the left fraction by 4. And remember, what I do at the top, I also do the bottom. And in order to get the same thing on the right fraction, I'm going to have to multiply the top and bottom of that one by x plus 2. So let's see what that gives us. So on the first fraction, the 3 times the 4 on the top gives me 12. And on the bottom, remember, the 4 has to multiply to both terms. We got to distribute it to everything. So 4 times x gives me 4x. And 2 times the 4 gives me 8. So I got a 4x plus 8 on the bottom there. Plus stays a plus. Then on the second fraction, I got to do the 5 times x plus 2. And again, I'm multiplying the 5 by both of them, distributing to everything. So that's going to give me 5x plus 10. And then on the bottom, I distribute the 4 to everything. So that's going to give me 4x plus 8. Once we've done that, we've gotten the common denominator. And then once we have the common denominator, then it's much easier. It's just getting to this point that sometimes gives us trouble. Because now I can go ahead and do the addition. And when I do that addition, I needed a common denominator because the denominator stays the same, of course. So I know my denominator is going to be 4x plus 8. Then on the top, I'm doing the addition, which of course means add the like terms. The 5x, it doesn't have any like terms. There's nothing else with an x in it in the top. So that's just going to stay a 5x. And then I'm going to do the 12 plus 10. And 12 plus 10 gives me 22. And then one last step with that, can it be reduced? Is there anything I can divide 5, 22, 4, and 8 all by? No. It's kind of close. It's almost 2, but I can't divide 5 by 2. So no, there's nothing I can divide all of them by. So that one is done. That would be your final answer.